All right, welcome back. Got a couple more examples to do. This is from the second worksheet, and hopefully you can follow along and have some fun with it. And again, I encourage you to watch a little bit and pause and think about these examples for yourself. So this one's a little bit unique. We've got a piece of cardboard or a piece of paper or something, and interpreting the question and starting it, I absolutely believe is the trickiest part. And it says we're going to make a box or a three-dimensional object by cutting out the corners of this. And if you have trouble visualizing it, I encourage you to get a piece of paper and cut the corners. And then the idea is if you fold them up, you're going to get kind of a box shape. And it says that each of these corners are, X units or something. All right. And we want to maximize the volume of, to put things into perspective, little X would be right here. Put things in perspective, we want to, I can't even speak, guys. Maximize the volume of the box. All right, long day. The volume in general is, base times width times height, or length times width times height, but I've got too many variables. But if I look at my bases here, the idea is that this length, once stuff is folded up, I believe is going to be 12 minus the 2x that I cut out. And same kind of logic over here. When I fold this side up, you've got 9 minus the 2x, or the two corners that I cut out. And when you fold it up or cut out your corners and try it on your own, the height of the box is just going to be whatever X units you cut out. And this is really cool because I know it's sloppy, but I think we just wrote all of these in terms of X. We have 12 minus 2x. We've got 9 minus 2x. And then the height we have is just X. And this is the only question I think you've done, that I've done, that only has one equation. We just kind of were clever and we manipulated it. And we're ready to take the derivative. Personally, I would distribute and maybe write this as 9x minus 2x squared. And I would distribute maybe one more time to try to get a cubic. And then after I distribute, then it's time for me to take the derivative and then set it equal to 0, and bada bing, bada boom. So check that out, and if you're having trouble seeing it, get out a piece of paper, cut out the corners, and try to fold it. Have some fun with it. All right, let's do one more. Number 8, kind of a beast of a problem. It talks about how there is a window that's formed from an open rectangle with a semicircle on top. And so interpreting the question is a little bit of a challenge in itself. But here's the picture of my window, right up here. And it says find the radius. So it'd be nice if I could write things in terms of r that will maximize the area of the window. All right, so that's telling me I'm going to for sure need a area formula. And it also gave a little hint that the perimeter of the window is 288. So I think I know what formulas I have to find. I have to find a perimeter equation, which is going to be equal to 288. And then I'm going to have to find an area equation. So before I find either one of those, you always need to either label your picture or look at a labeled picture. You need to put some variables on it. So I'm going to do this a little bit different perhaps, but I'm going to put an R here for radius. It's very tempting down here at the bottom to write x, but I want to try to keep it as with as few variables as possible. So if half of that circle is r, then here's a slightly efficient way. I'm going to put 2r down here. And then the side, you can list whatever variable you want. I like to use y for my vertical sides. And I think I'm ready to express some of these things. And so let's start with the area. The area is going to be 2ry. That's the rectangle. Plus pi r squared is the area of a circle. But I need to cut that in half because I want the area of a semicircle. And that is the equation that I'm going to maximize. But what I hope you see is we got too many variables. And I want r's, so r's are nice, but I have this y. And again, by now that should be kind of a thing that you can expect. You know, that's where the perimeter equation is going to come in. I need to find a y equation. Just to be thorough, this is my semicircle. So the perimeter is going to be 2r plus 2y plus the perimeter of the semicircle, and the circumference, I got too many formulas in my brain, is 2 pi r, but I only want half of that. All right, I'm getting closer. You can feel it. So I'm going to have 2r plus 2y plus pi r. All right. Remember over here, I wanted to solve for y. All right, this is what I need to fix. So I could use 288 minus 2r minus pi r. That's going to be equal to 2y, so I move that stuff over. And divide by 2. So I've really got 144 minus r minus pi r over 2 equals y. And it looks really messy, but when I distribute everything and simplify it, you're just going to have a bunch of power rules, I believe, I hope. So area equals 2r times y plus 1/2 pi r squared. So when you finish this, I hope you're thinking, all right, I just got to take the derivative. And you're just going to have to use the power rule. But for me, I usually distribute the stuff first, just to make sure that, for instance, I'm going to have 288r minus 2r squared minus pi r squared, because the 2's cancel, plus 1/2 pi r squared. And I'm ready to bust out the derivative. We're almost done. Set it equal to 0 and do it. So, all right. I hope I didn't make any mistakes because it's been a long week, like I said. If I did, politely let me know. But hopefully you can figure them out. I think everything's decent. I know for sure the process is, but if you didn't notice, there are some answers at the bottom of that handout if you scroll down a little bit, so you can kind of check it if you need to. So, thanks for tuning in, guys, and I'll see you later.